So today's lecture will be slightly tricky and maybe confusing. So please pay attention. Otherwise, you will not understand what I will be discussing today. Okay. So in the last lecture, what did we discuss? We said uh, whatever data or information we want to send, we have to convert it to binary because that's the only language which a computer understands. Now, when you convert it into binary, how do you ensure that the binary is decoded to the original information, right? Suppose if I am encoding AB, its encoding is 110, and if I am encoding F using this mapping, F's encoding is also 110. So I'm only sending 110 to the computer. How does it know whether I'm sending AB or F, right? Using this current mapping and the current method of sending just 110 will not work because the reverse process, that is decoding the original information from the binary code, you did not tell the computer how to do it. It is confused whether to treat this entire string as one unit or to break it into multiple parts, and if yes, how many parts. You didn't instruct the computer how to read that string. Okay, so the solution for that, what we discussed yesterday, was that to fix a chunk size, to have a basic unit which is a chunk of bits, and to force the computer to read these many bits at a time. So it cannot read 1 bit or 2 bits. If my chunk size is say 4, just for example, if my chunk size is 4, then it necessarily has to read 4 bits at a time. It cannot read less than 4, it cannot read more than 4. It has to read 4 bits at a time and treat these 4 bits as one unit, and whatever is the content in these 4 bits, that content maps to some character. Whatever is the number stored in these 4 bits, that number maps to a character. That is the idea. So once we make this rule, so now if I have to send F is 6. 6 requires only 3 bits, but it's not allowed. You have to use 4 bits. Whether the information takes 4 bits or not, whether the data requires 4 bits or not, you have to send 4 bits at a time. Okay, so although F takes only 3 bits, 110, you fill the remaining places with zeros. Okay, so you send 4 bits for F. Now, similarly, for sending AB, for A, I need 4 bits. For B, I need 4 bits. Okay, although A requires only 1 bit, it is only 1. But I cannot send just 1 bit. I have to send 4 bits. So I will fill the remaining bits with zeros. Similarly, for B requires only 2 bits, 1 0. But again, I will still send 4 bits. I will fill the remaining 2 places with zeros. So now for AB, I am sending 4 bits for A, 4 bits for B. So I am sending 8 bits for AB. So now there is no question of ambiguity. It will take 4 bits at a time. Whatever number is stored in those 4 bits, that number maps to some character. It will understand these 4 bits mapping to only that character and not any other character. Okay. And also there is no ambiguity with respect to the number of characters that I am sending. If I am sending 4 bits, I am sending only 1 character. If I am sending 8 bits, I am sending 2 characters. If I am sending 12 bits, I am sending 3 characters, because each 4 bits represent 1 character or 1 symbol. Okay. But in the previous case, here, say this 110, I didn't tell the computer what is the chunk size. So there are multiple ways of treating it, right? So you can treat this entire 110 as one unit, or you can divide it into 3 symbols, or you can divide it into 2 parts, 2 symbols in one part and 1 symbol in the other part, right? So you can divide it in any way you want. So now you don't know whether I have sent 1 symbol or 2 symbols or 3 symbols. The size or the length of the string does not tell you how many symbols I sent. I might have sent you 1 symbol, or I might have sent you 2 symbols, or I might have sent you 3 symbols. It's because I didn't tell you how to decode or how to split a binary string. Okay, but here I am clearly telling you how to split a binary string. So in this case, it is 8 bits and chunk size is 4 bits, and each chunk maps to a character. That's the understanding. Okay, but technically it's not 4 bits in the computer. It's just for example, in the computer it is 8 bits. Okay, so the minimum chunk size in a computer is 1 byte. You have to send 1 byte at a time. You cannot send less than a byte. You cannot send a few bits more than a byte. You have to send one more byte if you want to. You can't send just a few bits more than a byte. Okay, so we saw these data types. Suppose if my numbers which I am dealing with are very small numbers between 0 to 255, then I just need 1 byte. So I call that 1 byte with some name. I call it a char, because this can store numbers, small numbers between 0 to 255, as well as this can store characters, because characters take maximum 256 different values. Like if you remember the ASCII table and the extended ASCII table, even 7 bits are sufficient to store all the different ASCII values, because it goes from 0 to 127. Extended ASCII, some more characters are there, which may cover some European languages, but even for them, 8 bits are sufficient. Okay, so for the most frequently used characters, 8 bits, or even further more frequently used characters, just 7 bits are sufficient. Okay, so 1 byte is more than enough for me to deal with characters as well as with numbers which are very small. Suppose if I deal with values like people's age, 255 or 256 is a very large number. You don't need to go up to that also. So I can just use this data type to store these values. Okay, although the name is char, it is an integer whose size is 1 byte. That's the only difference. Char is an integer data type. Keep that in mind. Char is not fundamentally a different data type. Char is fundamentally an integer data type. The only thing is, this particular integer data type whose size is 1 byte is more often than not used to store characters. That's all. That's why it's called char. But a character is again fundamentally a number. There is no separate data or separate kind of data called character. It is fundamentally a number. But we are calling it char because we use it to deal with characters. That's the only difference, nothing else. Okay. So if someone asks you, what is the name of the integer data type with 1 byte? The answer is char, because char is also an integer data type. Okay. But if you take some other data types like float, we will see later, float or double, they are fundamentally different from integers. They are real numbers. Integer data type cannot store real numbers. Okay. So they are fundamentally different. Char is not fundamentally different from integer. Instead of char, I can as well call it a short int. That's all. Only thing is, short int is used mostly to deal with characters. That's all. Okay. So after char, if I have larger numbers greater than 255, if I have to deal with 256 or 257 or 500 or 1000 or whatever, I need minimum 1 more byte, not just 1 or 2 bits. Technically, yes. Suppose if I want to store 256, I just need 9 bits. But I can't give 9 bits to a computer because I'm dealing with blocks, I'm dealing with chunks. So after 1 byte, I need to add at least 1 more chunk. I can't just add a portion of the chunk. So after 8 bits, I have to jump to 16 bits. Whether I want only 9 bits or 10 bits, I should still use 16 bits. Okay. So that data type whose size is 16 bits, that is short int. So why short int? This deals with integers, and now this can deal with numbers of a higher range than 256. Since I have 16 bits, I can store 2 power 16 different values, and the range will be 0 to 2 power 16 minus 1, right? So let's see what is 2 power 16 minus 1. Just this 65,535. So this is the maximum number that can be stored in short int. The maximum number that can be stored in char is 255. The maximum number that can be stored in short int is 65,535. But we many times deal with even larger numbers, right? So now even 2 bytes are not sufficient. I want more. Now, the smallest increment that I can make to 2 bytes is one more byte. Adding one more byte, it will be 3 bytes. But if I keep adding only 1 byte at a time, I need to have so many data types for every small range of numbers, right? So rather than increasing these bytes linearly, we increase them geometrically, like 1 byte, then 2 bytes, then 4 bytes, then 8 bytes, then 16, and so on. Okay, so after 2 bytes, next I will deal with 4 bytes. 4 bytes means how many bits? 32 bits. 32 bits means how many different values? 2 power 32 different values. The range is from 0 to 2 power 32 minus 1. So let's see what number we can capture using 2 power 32 minus 1. That is this. Now it's a very big number. So up to these numbers, so if you know your numbers fall, if your numbers are greater than 65,535, then you use int. Short int will not be sufficient. Suppose if my number is 1 million, 65,535 will not be sufficient. I have to move to int. Okay, and this is in the range of maybe billions. Even if this range is not sufficient to you, then from 4 bytes you go to next step is 8 bytes. That is long int. 8 bytes means how many bits? 64 bits. So 64 bits means the range will be from 0 to 2 power 64 minus 1. That is this. Okay, so this is very big. For many practical purposes, this is sufficient. When you're dealing with integers, we will get into float and double later, real numbers later, but for integers, this is more than sufficient. Usually int is sufficient. For many practical purposes, int is sufficient. So the point is, you have to add minimum 1 byte at a time. Okay, technically I can also have a data type with 3 bytes. I can also have a data type with 5 bytes. That's okay. But practically, that is of no use. It's like making smaller jumps. Once I make a jump, then I make next a slightly larger jump, then again slightly larger jump, so that with 3 or 4 data types, I cover maximum cases. So with char and short int, and long int. There is also long int. Let's not worry about that. Minimum these 4 are more than enough to handle integers. Okay. All right. So this is the syntax in C. So suppose if I want to store some number 5 and I want to reuse it again and again, I will store it in some variable, say x. Now this x I will use later, maybe to do x plus y or multiply x with something or to, yeah. Okay. Okay. Yeah. Yeah. So suppose if I want to store a value, say 5 in some variable, right? And I want to use this variable again and again later. So I call it x and I can use it in any equation, or I can even override this variable with some other value. I can do anything I want. Now, when I am storing this number in the computer should know in what format I am storing it. It's like, am I storing it as an integer, or am I storing it as a real number, or am I storing it as some other data type? You will understand real numbers format later, but the computer should know, okay, how many bytes should I allot it, and in what format should I store it? Okay, these two things computer should know. Right now, we will only focus on the bytes. How many bytes should I allot it? So I am saying it is an integer, so it will allot 4 bytes. Although the number 5 is very small and it requires 5 binary representation is what? 101. You see, these should be at your fingertips. What is the binary representation of, say, at least first 8 decimal numbers? Okay, so 5 binary representation is 101. It requires only 3 bits. So the minimum chunk is anyway 8 bits. So actually I can do with 1 byte. I can do with 8 bits. But suppose I am saying int, it will allocate 4 bytes. So only the rightmost bits will be 101. All the remaining 29 bits will be zeros. Okay. You need to tell what data type it is, what data type the variable is. Okay. You can use shortend, you can even use char for this. Okay. It's up to you. But usually we use int because what if in future in this program I may need to deal with larger numbers. If I use char, even if by mistake I use some number, say 1000, I forget that I used char. I cannot store 1000 in that. So let me use shortend. But again, if you use shortend, what if I use slightly larger number than 65,535? I may deal with a million. Again, why getting confused later? Let's use int so that all, all practical purposes, all integers that we use, they will be covered in that. Okay. So that's one thing. And similarly, maybe some other variable you want to declare, say ch. Again, you have to specify its data type. That is a character. Character is nothing but a single byte integer. There is no separate data type for 1 byte integer and separate data type for 1 byte character. Char itself is 1 byte integer. Okay. All right. So this is just basic syntax. You declare the data type as well as the variable name. In other languages like Python, you don't need to declare the data type. You don't need to say it's int or char or whatever. You just say variable name and the value. You assign a value to it. It will try to guess the data type from the value you're assigning to it. Okay. But here you have to specify the data type clearly. Fine. That's the thing. Okay. Now we need to deal with. So far, what did we deal with? We only dealt with positive numbers, right? We only dealt with positive integers. So now the question is, what about negative integers? For this, we discussed a solution. What did we say? Yeah. So this is only one solution. So what did we say? We said, say out of n bits, reserve 1 bit as the sign bit. Okay, so let's say I have 1 byte, that is 8 bits, right? Okay, so out of these 8 bits, I will say these 7 bits represent the magnitude, and this bit is a sign bit. So sign bit in the sense, it's up to me. I can assign, say 0 for positive and 1 for negative. All right. Now, what is the range of numbers that this can represent? Okay, first let's just take these 7 bits alone. All right. Now, if I consider only these 7 bits, okay, what is the range of numbers this can represent? 0 to 2 power 7 minus 1. Now, I have an additional bit that will give me both positive as well as negative numbers. Now, if I include this sign bit, what is the total range of numbers I can represent? Minus 2 power 7 minus 1 to plus 2 power 7 minus 1. Right? Suppose if this sign bit, I don't use it as a sign bit, but I treat all the 8 bits as magnitude. Okay, then what is the range of numbers that I can represent? 0 to 2 power 8 minus 1. Okay, so now you get the pattern. Suppose if my data type has n bits, okay, if all the n bits represent magnitude, then my range is 0 to 2 power n minus 1. Okay, suppose if among them one bit is a sign bit, then my range is minus 2 power n minus 1 to 2 power n minus 1. Sorry, 2 power n minus 1 minus 1 to 2 power n minus 1 minus 1. Minus of 2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. Okay, so what is happening? Your positive range is getting halved. If you, in the previous case, if you can represent 2 power 8 numbers, positive numbers, say including 0, let's say it is positive, doesn't matter. If you reserve one bit as a sign bit, then you can represent only 2 power 7 positive numbers and 2 power 7 negative numbers. If you have 32 bits, without the sign bit, you can represent 2 power 32 positive numbers, but with the sign bit, you can represent 2 power 31 positive numbers and 2 power 31 negative numbers. Okay, so that is what is happening. Fine. So this is usually represented in computer in the data type. For each data type, particularly integer kind of data types, there are two subtypes. That is called, does anyone know? Signed and unsigned. So signed int and unsigned int. Signed char, unsigned char. Signed shortened, unsigned shortened. Each of these will have both signed and unsigned types. If you know the data you are going to deal with includes only positive numbers, it doesn't include negative numbers. There is no need to deal with signed numbers, right? Signed integers. Signed means it will deal with both positive and negative integers. Unsigned means it will deal with only positive integers. So unsigned means all the 32 bits will be reserved for magnitude. There is no sign bit. Signed integer means one bit is reserved for sign. The remaining 31 bits are reserved for magnitude. Okay. So unsigned int range will be 0 to 2 power 32 minus 1. Signed int range will be minus 2 power 31 minus 1 to 2 power 31 minus 1. Okay. Yes, that is one thing. Now, when you write just int, int is also fine. It's not necessary that you have to specify always whether it is signed or unsigned. If you don't specify, by default, it will take what? It will take signed. By default, it will take signed. So signed is optional. But if you want to deal with unsigned, you have to write it unsigned. Okay? Fine. Now, suppose if I am dealing with small integers in the sense, say, minus 127 to 127. Okay, then what should I use? What data type should I use? Char. Char, whether you write signed or not, it is signed only. Okay, so when you write char, it will deal only with this range of numbers. If you want to deal with, say, 0 to 255, you have to write unsigned char. Okay. So now this char can be used. So char x equal to maybe, minus 23. Fine. Now I can do x plus y, whatever it is, I can do all those things. I can also say char x equal to say M. This M looks like a character to us, but technically what it is doing, it will go to the ASCII table, find the, so let's look at some character whose ASCII value we know, say small a. Small a's ASCII value is 97. Okay. So when I say char x equal to small a, what it is doing, this is equivalent to saying char x equal to 97. That is what it is doing. That's all. It will store this a as 97, convert it to binary and store that in the computer. That's it. Okay. So I can do a plus b, a minus m. I can do these things also. So basically what will it do? It will take the ASCII value of a, it will take the ASCII value of m and do the subtraction. That's all. That is why char is fundamentally an integer data type, but a small integer. That's all. For us, for it to be easy for us, rather than storing the ASCII value of finding the ASCII value of a character and then storing it and then again converting it back to the character, which character are we dealing with, to avoid all this trouble, we are given an option in C programming to directly assign the character. I'm assigning A to this variable, I'm assigning B to that variable, so that I know I'm dealing with AB. Otherwise, I need to remember ASCII value. I'm assigning 97 to this, 98 to that, something else to something. Okay, what ASCII value is this? That's a headache for me, right? So fundamentally, they are ASCII values only, but just to make it easier for us, we are typing a character. Okay, so when you store a number, you can print either the number as it is or its corresponding character. Similarly, when you store a character, you can either print the character as it is or its corresponding ASCII value. Anything is fine. It is finally storing a number only. Okay, how you print it, how you represent it is up to you. All right, that's the only difference. Okay, now all right, this is fine. That okay, there is a sign bit and the remaining bits represent magnitude, but so suppose I have 8 bits, 1 byte. Now how many unique different values can I capture using 8 bits where 1 is a sign bit? Is it 0 to 255 or minus 127 to 127? Where one of them is a sign bit, the remaining are magnitude. Minus 127 to 127, right? But so how many unique values are there? $255 or 256? $254. Why 255? Why not 256? Yeah, because there are two representations for 0, plus 0 and minus 0, right? But both of them mean 0 only. There is no concept of plus 0 minus 0, right? So but 0 has two representations. So what are they? Plus 0 is represented as what in 8 bits? 0. 0 followed by 7 zeros. That is 8 zeros, right? Because the first bit is positive. Okay. Minus 0. 1 followed by 7 zeros. Okay. So there are two representations. Now there are two issues. One is it is ambiguous. When I see this representation or this representation, it's the reverse is not ambiguous, but how do I store a 0? that is ambiguous. Should I store it like this or should I store it like this? That is one thing. The second thing is waste of space. You are unnecessarily wasting space to store the same number. All right. So normally what we try to do, we try to squeeze the maximum amount of space. You know, even one byte is important. So we don't want to waste even a single byte, right? So what to do? Can we have a unique representation for 0? Not two representations, one for plus 0, one for minus 0. Among these two representations, can we keep one representation for 0 and another representation for something else? Okay, so you most probably will not know the answer because it's slightly difficult. So that's what I said will be confusing for you. So let's get into that. So before that, so let me mention the problems. So one is ambiguity. Second is memory wastage. Third, you will not understand today, you will understand in the next lecture, but I'll just mention it. Uniform method for addition and subtraction. Okay, this third one, don't worry, you won't understand now, you will understand by tomorrow, by next class. Okay, so the solution for this is in something called, R's complement. So before I tell you the uses of it, let's first look at some examples and then you will understand how it is useful in a while. So just give me some time, I'll explain its use by the end of this class. Okay, so how do you calculate R's complement? So first let's look at individual terms. R is base of the number system. This is also called radix. And capital N is whose complement we want to find. See, it is a good habit to note down things. Okay, don't just sit as if you're sitting in the movie theater. Please note down so that something will go into the book and also into your head. Small n is number of digits in n, and the formula for R's complement of n, capital N, in base R is R power small n minus capital N. Okay, don't get overwhelmed, it's quite simple, nothing complicated. So let me take a couple of examples and you will understand immediately. Suppose I have, say, number 7 in base 10. Now, what is R here? 10. What is capital N? 7. What is small n? 1, right? So 10's complement of 7 in base 10 is, what is the formula? R power small n minus capital N. So here it will be 10 power 1 minus 7. That is nothing but 3. Okay. So 3 is tens complement of 7. Okay, let's take another example. (247) base 10. Again, here R is 10. Capital N is 247. Small n is 3. So what is tens complement of 247? 10 power 3 minus 247. So how do you write it? 1000 minus 247, right? So here what do? We do carryovers, right? So this one, when it goes here, what does this become? 10, not 0. 10, right? From this 10, you carry a 1 to the next place. So this 10 will become 9. And this will become 10. From this 10, you carry a 1 to the next place. So this 10 will become 9. And this will become 10. Okay? So 10 minus 7, 3. 9 minus 4, 5. 9 minus 2, 7. This is 0. Okay? So the answer is 753. So now 753 is tens complement of 247. So 753 is tens complement of 247. Okay. Now you see, subtracting something from 1000 or 100 or 10,000 or any power of 10 is too cumbersome, because every step you need to take a carryover. All right. So let's try to make it a little easy. So what we will do, we will write this 1000 as 999 plus 1 and subtract 247 from this 999, and whatever is the result, we will add 1 to it. Right? Now subtracting from 9s is easy. Any digit will be either equal to or smaller than 9 in decimal system. Right? So 9 minus 7, 2. 9 minus 4, 5. 9 minus 2, 7. 752 plus 1, 753. You again got the same result. Fine. So 752 is called 9's complement of 247. Okay. Now this 753, which is 10's complement of 247, is equal to so let me move into the next page. Or let me just write 10's complement of n is equal to, can anyone guess what is the, in terms of 9's complement? Exactly, 9's complement of n plus 1. Fine. So it is easier to calculate 9's complement instead of calculating 10's complement. We will calculate 9's complement, add 1 to it, we will get 10's complement. Fine. Now, why did we get 10's complement? What is the use? Okay. So I'll give you an example of where 10's complement is useful. So let's say I want to do some subtraction, 532 minus 247. Yeah. Yes. Yes, you can. But then that's of no use, because 8's complement, what if you have 9 in the subtrahend? You need to do carryover again. That's why take the maximum digit in that decimal, in that number system. In decimal system, 9 is the maximum digit. So take the top one to be made up of all 9s. So that the bottom one, whatever digit it has, you don't need to take a carryover in the top one. You just do a direct subtraction and add 1 to it, you will get the original result. Okay. All right. Now suppose I want to subtract these two numbers. So what do we do? This I will write as 532 plus minus 247. Okay. This I will again slightly modify it as 532 plus 1000 minus 247. I brought in 1000. I need to remove it. Minus 1000. But what is this? Right. Tens complement of 247. We just calculated the tens complement of 247 is 753. So what we will do? We will do 532 plus 753. So what will this be? 5, 8, 12. Now I need to do minus 1000. This will be 285. Or another way is, once I get 1285, I just need to discard this one. I will get 285. I just need to discard the carryover. Is it the correct answer? 532 minus 247. 12 minus 7, 5. This will be 2. 1 carryover. 12 minus 4, 8. This will be 4. 4 minus 2, 2. You see, I got the answer. I got the correct answer. So what is happening? You are finding the result of the difference not by subtracting the original numbers, but by adding two different numbers. Okay. Now you may say, but in the process of finding tens complement, we are doing subtraction. Yeah. You may say, we are not completely doing away with subtraction. Although original numbers, we are not subtracting one from each other. To find the tens complement, we are doing subtraction, right? Either from 1000 you are subtracting 247, or from 9's complement you are subtracting 247 and adding 1 to it. There you are doing subtraction. So somewhere you are doing subtraction. So you are not completely doing away with subtraction, right? So that question is there. Fine. That is there in decimal system. But in binary system, we will completely do away with subtraction. We will addition. You will anyway do addition of two numbers. Subtraction of two numbers also you will convert into addition of two different numbers and get the correct result. Okay, so basically whatever circuit you built for addition, same circuit you can also use for subtraction, because computer is made up of all circuits only, right? Gates, logic gates, AND gate, OR gate, NOR gate. We will look at them in the next lecture. But you don't need to build a different circuit for addition and different circuit for subtraction. You can use the same circuit which you built for addition to do subtraction also. Okay. Now here again you may say, okay, but 2's complement, to find 2's complement of a number you need to do subtraction. To find 1's complement of a number you will need to do subtraction. What about that? We don't need to do that. I will show you that in a moment. Okay. Yeah. Before we move on, let me take another small example. Suppose I just want to do 6 minus 3. Okay, one is I actually subtract 3 from 6, I will get 3. But another way is I say 6 minus 3 is 6 plus of minus 3. That is nothing but 6 plus 10's complement of 3. And what is 10's complement of 3? 7. 6 plus 7 is 13. I got an additional carryover. Remove it. I got 3 finally. Right? The answer is correct. Final answer is 3. You ignore this one. Take the remaining digits. That will be your answer. Okay? Now, what if I subtract a larger number from a smaller number? Again, this I write as 3 plus minus 6. That is 3 plus 10's complement of 6. Yeah, that is 3 plus 4, 7. But the answer should be minus 3. So how do I Connect 7 with minus 3. Huh? 7 minus 10, right? So what we say, we know this is a smaller number, this is a larger number. So the result will be negative. So put a minus sign. Whatever is the result of this addition of complement, you find find tens complement of the result. That will be 3. So put that 3 here. If you are subtracting a larger number from a smaller number. If you are subtracting a smaller number from a larger number, you will get a carryover. Just discard that carryover. So two different cases. If you are subtracting a smaller number from a larger number, like 6 minus 3, you will finally do 6 plus 7. You are getting 13. Ignore this one. The answer is 3. But if you are subtracting 3 minus 6, then you are getting no carryover. You are getting some digits. Find the complement of the result and put a minus sign before it. That's all. Okay. Now let's do it for binary. Okay. So let's take a number like say 13. 13 in binary. Okay. Sorry, this is in decimal, but in binary, what is this? What is the binary representation? Huh? Yeah, 1101. Okay. Now here, what is R? What is R? What is the radix? 2. What is capital N? 1101. Now you are dealing everything in binary. What is small n? 4. So what is 2's complement of this number? How do I calculate? 2 power 4 minus 1101. This 2 power 4 is in decimal. That is 16 in decimal minus 1101 in binary. I need to convert 16 to binary. 16 in decimal is what in binary? What is binary representation of 16? What is 16 in terms of powers of 2? 2 power 4. So 2 power 4 means what? 1 followed by 4 zeros. That's what 10 power 4 means, right? 10 power 4 means 1 followed by 4 zeros. In binary, 2 power 4 means 1 followed by 4 zeros. So 1 followed by 4 zeros minus 1101. Now again we need to do carryovers. Okay. This 1, when it is carried over here, what will we get? 10. Okay. Let's say 10. This 10, when I remove 1 from this will become 9. This will become 10. This 10 again, this will become 9. This will become 10. Okay. Now this 10 again I remove a 1. This will become 9. This will become 10. Now what will be the result? 10 minus 1, 9. 9 minus 0, 9. 9 minus 1, 8. 9 minus 1, 8. Is this the answer in binary? So where are we making the mistake? This can't be a binary number, right? Binary system doesn't have digits 8s and 9s. Huh? 10 means 2. Exactly. So just because you are used to something doesn't mean that will fit everywhere. Okay. So when you carry over a 1 from a higher place to a lower place, it becomes 10 only in decimal system, not every system. In this system, when you carry over a 1 from a higher place to a lower place, it will become 2. Because here the base is 2. There the base is 10. So decimal system is just like any other number system. Implicitly, you are dealing with tens. That's all. That doesn't mean every number system will be like that. Okay. So here the logic will be when you carry over this 1 here, it will become 2. Now you subtract 1 from this 2. it will become, this will become 1. Here you get 2. When 1 comes here, this 1 0 in binary is what? 2. 1 0 in decimal is 10, but 1 0 in binary is 2. Okay. From this 2 you subtract 1. This will become 1. This will become 2. Again from this 2 you carry over 1. Remove 1 here. This will become 1. This will become 2. Now 2 minus 1, 1. 1 minus 0, 1. 1 minus 1, 0. 1 minus 1, 0. This will anyway become 0, 0. So what is 1, 1? 3. This original number is 16. This number is 13. So we got the right answer. So you can do binary subtraction in binary system also. You need not convert them to decimal and then do the subtraction and then convert the result to binary. No. Decimal system is just like any other number system. If you can do it in decimal system, you can do it in any other number system. Okay. So let's say in octal system, when you carry over a 1, what will it become? 8. Okay. And so on. Fine. So now let me quickly. So now again, many carryovers are there. This is too much of a job. So I will write this 16 as 15 plus 1. Okay. 15 in binary is what? 15 in binary is 4 ones. 1, 1, 1, 1. And I'll say plus 1. This is 16. From this 1, 1, 1, 1, I'll subtract 13. 1, 1, 0, 1. And whatever is the result, for that I will add this 1. Okay. So 1 minus 1, 0. 1 minus 0, 1. 0, 0. So this is 2, right? 2 plus 1, 3. I got the same result. So here 2 is 1's complement of 13. Okay. Here 3 is 2's complement of 13. And again, 2's complement of a number is equal to 1's complement of that number plus 1. Fine. Now, how do I find 1's complement? We may think, okay, we need to do the subtraction. No, in binary, finding 1's complement is extremely easy. You just see if 1101 is my number, for its 1's complement is 0010. So do you see a pattern? What? You are just flipping the bits. 1 becomes 0, 0 becomes 1. So there is no subtraction here. So when given a binary number, find its 1's complement by just flipping the bits and then add 1 to it to find the 2's complement. Okay. Now use this 2's complement to do the subtraction, in the sense add this to the original number. So if I have to do 16 minus 13, I will do 16 plus of minus 13. 16 in binary is 1 followed by 4 zeros, plus complement of 13 is this 0010. So I will add this 0010. What will I get? This thing. Ignore this one. What is remaining? 2. No, this is 1's complement. I need to add 1 to it. So for 13, 2's complement is 1, 1. This I should use. Okay. So 0011. Finally, I will get this one. So I got the right answer. Right. Suppose if I have to do 13 minus 16. Then what do I do? 13 I'll keep as it is. I'll find the 2's complement of 16. 16 is 1 followed by 4 zeros. Find its 1's complement first. That is 0, 1, 1, 1, 1. Add 1 to it. What you will get? You will again get 16. So 16 is a special number whose complement is the same as that number. Okay. So 1, 0, 0, 0, 0. You will get 1, 0, 1, 1, 1. Okay. So now find the complement of this and put a minus before it. Find 2's complement of it. First, to find 2's complement, first find 1's complement. That is 0, 0, 0, 1, 0. Add 1 to it. That is 1, 1. Put a minus before it. What is that? Minus 3. So you got minus 3. 13 minus 16 is minus 3. Okay. So only 2 cases. If you are subtracting a smaller number from a larger number, that is like adding the smaller number's complement to the larger number. In the result, you will get a carryover. Ignore the carryover. The remaining bits or the remaining digits, that's your answer. The second option is you are subtracting a larger number from a smaller number. In that case, you will be adding the complement of the larger number to the smaller number. in the result, you will not get any carryover. The entire result you take, find its complement and put a minus symbol before it. Okay. Now, so the point is, now there is no point of subtraction. Even while finding one's complement, you're not really doing subtraction. While finding two's complement, you're not really doing subtraction. So you don't need a separate circuit for subtraction. You just need one circuit for addition. And even to do subtraction, you can do that as addition of complements. So while finding complement, you're not doing subtraction. While adding complements, you're not doing subtraction. Once you get the result, you're just discarding the first bit. Even that is not involving subtraction. Or you're finding the complement of the result and putting a minus. Minus is just to write on the paper for us to understand. Otherwise, that number, whichever it is actually complement of the original. That number will be treated as -3. So this binary sequence 11101, it will be stored as it is in the computer, but it will be understood as -3. Okay, you will understand that later, but that's the purpose of complements. This will be covered in a little more detail in tutorials. Fine.